So welcome all to week 9 tutorial for the course Deep Learning. I'm Pintu Kumar. I'm a PhD scholar at IIT Bombay. So today we are going to cover a wide range of topics related to NLP. Okay. So we are going to cover why do we require representations for NLP tasks. Okay. So I think this and RNN would be two modules on NLP in this course of deep learning. So we are going to talk about word representations, like what is the need of it, and we'll also talk about some of the classical methods for word representations, and some of the methods that are proposed based on deep learning models. We'll also discuss about them. Okay, and we'll also give some time to how do we evaluate representations. So when you did like classification or regression tasks, what you used to do is you used to withhold some amount of validation or test data set, and you used to check its performance on that kind of data set. But if you are converting your words or sentences to some vectors, how do you judge the quality of those kind of vectors? That is another question. So we'll try to discuss that also. Okay. And one very small thing that I want to mention is that these lectures were recorded like at least I think 3-4 years back. Okay, at that time this globe or word to vec or skip gram was very common, and people were using that a lot, right? Still at industrial level, so many industries are using these kind of models. But when you see the research domain or academic domain, or if you look at applications like chat gpt or those kind of things, they actually are not using these kind of representations a lot. They have switched to something that is known as transformers. So because these lectures were recorded earlier, transformers are not covered here. So like for completeness, you might refer to some other sources where you can see what are transformers, how do they work, and how do people use them to find the word representation and those kind of things, or to do NLP tasks. Okay, so you can refer to something that is known as transformers. That would be useful in today's context to you. Okay, so these are few things. Okay, that we're going to cover. Okay, so first of all, this whatever we are going to discuss today can also be covered in a broad umbrella of something that is known as representation learning. Okay, so I'll just give you a brief 3-4 minutes introduction about what is representation learning. It might be pretty useful for you. Okay, because this course is a 12-week course, like, yeah, but so we can't cover a lot of content here. So but it might motivate you to see other resources. Okay, so what is the broad umbrella of representation learning? I'm very loosely speaking over here, but what is representation learning? Representation learning is something in which you modify your data. Okay, so you modify your data into form where learning is easier or better. Okay, so I'll give you a very interesting example that I found interesting is, let's say you are dealing with Roman number system. Okay, so you remember in school you might have done something like this represents 5, this represents 10. Let's say I ask you to add these two numbers. Okay, so what you will do is you'll straight away tell me that the answer is 15. Okay, I don't remember the exact representation, but it should be this one. Okay, but what in your mind you are doing is you are first converting this text, whatever is written over here, you are converting this to your decimal number system. You are converting this also to your decimal number system, then carrying out the addition, then you are getting the answer 15, and then you are converting it back to your Roman number system. Okay, So for your mind to do addition, decimal number system is a better representation of numbers as compared to your Roman representation. Okay, this is a simple point that I wanted to make. So in representation learning, the whole point is to find better representations or to modify your data in such a form that your learning tasks become easier or better. Okay, so now let's come to this domain of words or text that we are going to discuss today. So let's say you have some words, or you have some sentences, or for that matter, you can even have some complete texts. Okay, so let's say some PDFs or those kind of things, or complete document. Okay, and you want to pass them through some machine learning model. Okay, or some deep learning model. So one thing is that you haven't seen any algorithm that specifically deals when you give it words as input. Okay, you have seen algorithms where you give vectors as input, you can process that data and you can get the output, but you don't know any method where you can explicitly enter words and it will give you some output. Okay, now this is not only true about words. Okay, so the similar thing is even true, let's say when you're dealing with some network data. I'll just give you an example so that it broadens your horizon. Like you can approach even network data in this by this approach. You can approach some biological data using this approach. I'll just motivate that. Okay, so in network data, what you have is you have some graphs where you have some nodes as well as some edge connecting those nodes. Okay, and you want to apply machine learning on these kind of data sets. Okay, another example can be, let's say you have some DNA sequence. Okay, they also look as something like KL. You have a sequence of letters that you have, and you want to make some predictions on these DNA sequences. Okay, and you might encounter many different kind of data sets in world. For example, speech data set, right, where you will have waves, right? For example, speech data set. Okay, so how do you tackle these kind of data sets? How do you apply machine learning algorithm to these data sets? So there are two possible paths that I can think of. Okay, so first path is that you design methods specifically for these kind of data sets. When we'll see CNN or RNN, you will realize that CNN is sort of exclusive to, at least it was proposed in a way that it was exclusive to image data set. RNNs were exclusive to sequence data set. At least it was proposed in that way. Then people found many applications here and there, and they do a lot of things. But there are some methods that are designed specifically for these kind of data sets. So what you will do is you will design some methods that are specifically for your your natural language processing task. You will design some methods that are specifically for networks. For networks, there are methods like graph, convolutional network. You might have heard of this. These are called GCNs. There are methods like node to vec or those kind of things. Okay, so these are not specific methods, but GCNs are specific methods. Okay, there are message passing algorithms that are specifically for graphs. Okay, then you can have specific methods again for DNA sequencing or speech data sets. One path is that you design specific methods for the data set that you have at hand. Second uh, path that you can take is you convert your data set to such a representation where you know the algorithms that you have at hand. For example, you know how your normal neural network works. So what you can do is you can convert these data sets to some Rn vectors, and then you have a variety of models that you already know, and you can use them. Okay, so the advantage of using this second path is that you already have a lot of literature available with you. You have already have a lot of methods available with you. People have analyzed those methods. You know where it is gonna do good, where it is gonna do bad. So you can use all these knowledge if you just find a way to convert your existing data set to an Rn vector. Okay. Also, one more point that I want to make over here is, uh, let's say somebody says that we don't want to convert this vector to Rn, right? But we just want to pass the like, let's say you have this word. What you do is, let's say for word cat, what you do is you say this is my third word. Okay, this is my first. This is some, let's say, I don't know what it is. Let's say this is 18th number in my alphabet. I can represent cat by this, right? This is C80 cat, right? So these are just symbols. C represents the third quantity in my like alphabets. The A is my first number, and T is some number, right? So rather than writing this way, some people can propose that we just write it in this way, then we have numbers, and we can process this kind of data set too. But again, the problem with that would be is that you don't have words of same length. Okay, so you can have cat and you can have tiger. Okay, so the length varies in both of them. Okay, so if you can recall, when we had neural networks, we had input layer of fixed length. Okay, so right now we don't know any method where our input like input dimension can be a varying dimension. So we want a fixed dimension for all the inputs. That is another reason where we want to convert it to some Rn vector where your n is some fixed number. Okay, so this might not be very useful for word representations, but there are many kind of data sets where you will want to convert it to some Rn representation only because the data set that you are encountering are not of fixed shape or size. Okay, so that is also a possibility that I want to point you to. Okay, so this was the motivation for sort of representation learning, or why do we want to convert text data to some Rn. Okay, so what are the two takeaways from it? First takeaway is that you can take both these paths. You can design methods specifically for those kind of data sets, or you can convert your data sets into Rn representations. Okay, so if you convert your data set into Rn representations, you already have a lot of content. I would say a lot of techniques available with you. People have analyzed those kind of techniques. You know the drawbacks and the positives and negatives of those kind of techniques. So it's easier for you to work in that kind of domain. Second is, if you have a data set that suffers from this varying size or shape problem, you can just convert it into sub Rn and you can get your result. Okay. Okay. Any doubt in this? What is the motivation behind converting this to Rn? Yeah. Any doubt in this? We can discuss, like, if you want to ask anything here. Okay. So again, I have mentioned this thing before also, but I'm reiterating it, that these lectures were recorded sort of, these are not very new lectures. These are at least 4 or 5 year old lectures. I'm not sure about the exact timeline. Okay. So these methods are not very new ones. You can refer to YouTube or other resources for much newer methods. So there are transformer based methods. You might have heard of something called as BERT, which is very common these days. So this is bidirectional transfer. So you can have a look at these kind of techniques. Okay, so just to sort of have it in your bag, and if it is required at some times, you can use it. Okay. Okay. Now we'll just stick to something known for, now we'll stick just to text data. Okay. And the first method that I want to discuss uh, to convert our uh, text to Rn representation is known as one hot representation. Okay. So how does this NLP community sort of, I'll try to define some terminology before we get into it. Okay. So first thing is something that is known as corpus. Okay. So what is corpus? Corpus is the collection of all the texts or the files that is available with you. For example, if you talk about something called Wikipedia corpus, so Wikipedia corpus would contain all the Wikipedia pages that are existent. So you will collect all the sentences, all the words, or all the files that are present over there, and that will form your corpus. Okay. This is something called as vocabulary, and that is represented by V. Okay. So what is a vocabulary? Vocabulary is a set of unique words in your corpus. Okay. So let's say if you want to find the vocabulary of, so whatever is written in the highlighted portion, so vocabulary would contain 1, 2, 3, 4, 5 words. It would be one hot representations, corpus, and vocabulary. These would be my 5 words in my vocabulary. Okay. So what is the basic idea behind one hot representation is, first of all, you form a vocabulary set. Okay, so this is a V. So this is some example where your vocabulary words are human, machine, uh, interface for computer, and so on. Okay, and you want to represent the word machine. So what you will do is, so you will number these positions. So first position is human, second position is machine, third position is let's say interface. Then you will have one at the place. So if your word is machine and it is listed at second position in your vocabulary, so you will have one at the second position and you will have zero elsewhere. This is known as the one hot representation. Okay. So this way you can find representation of every word in your vocabulary. Okay. So there are some problems associated with this method. First problem is that let's say you talk about Wikipedia corpus. Okay. So your Wikipedia corpus would have almost every word in your English dictionary, if not all, but it will have very large number of words. It would be in some millions. Okay. So because your length of your vector is equal to the number of words in your vocabulary, so if your number of words in corpus is large, then the vector dimension of this one hot representation would be very, very large. Okay. So this is one problem. And second problem is that they don't carry any notion of similarity. Okay. So what do I mean by the second point is that they don't carry any notion of similarity. Let's say there is a boy or a girl. Okay. There are 3 words, let's say. Okay. There is a boy, there is a girl, and there is a truck. Okay. So if you look at boy and girl, you can say among these 3 words, these are somehow related to each other. They both refer to some human being. They both have 2 legs. They both have some emotions and many other things you can say. They are very related to each other. You can't find this kind of relation between a boy and a truck. Okay. So what we want is the vector that we are finding for boy. Let's say this is VB. Okay. So what we want is my VB should be close to VA, sorry, to VG as compared to, so this is what I want, right? That if my 2 words are related in sense of English grammar or English dictionary, then their vector should also be close to each other. Now this, what do I mean by this close? People can have different notion for this close. Some might use cosine similarity. Some might use Euclidean similarity or Euclidean distance. That is up to the application that you're working with. Okay. But I want this thing, there should be a sense of closeness between the words that are related in English. Okay. So, but this one hot representations fail to do justice to this kind of expectations. So they do not capture any notion of similarity. Okay. Okay, here is a question. This is a simple question. So we are given the one hot representation of two words. First is apple, second is ball. What is the Euclidean distance between apple and ball? Okay. So this is a pretty simple exercise. So Euclidean distance would be square root of 1 square plus 0 square plus 0 square plus 1 square plus 0 square, right? It would be square root of 2. Okay. This is an easy question, but if you look at any two arbitrary one hot representation, then you will always get square root 2 Euclidean distance between these two. Okay, this is the point that I was making, that they do not capture any notion of similarity. Okay, and also like if you use cosine similarity, then the value of cosine similarity will always be 0. Again, this also is not able to capture any notion of similarity. Okay. So this was the first and the most basic form of representation, that was one hot representation. Second method of representation that people can use is something that is known as co-occurrence matrix. Okay. So now, like, I'll just give you an example. I'm thinking of one. Uh, okay, so let's say there are okay. We can have these two words, those two sentences. Let's say you write something like this is against my principle, and you say that you were called by your school's principle. Okay. Now there are two words in English which are pronounced almost similar. They are pronounced similar. That is principle, and they both have slightly different spelling, but and also different meaning. Okay. Let's say somebody don't know, or your algorithm don't know which what is the correct spelling of this principle and what is the correct spelling of that principle. Okay. And there are some words in English dictionary which are written exactly the same. They might be pronounced slightly different. Their spelling is same. They are pronounced differently, and they have totally different meaning. Okay. So that is also a possibility. So even if you don't know which one is the correct spelling, I might have made a mistake in writing the spelling. But because if you look at the complete sentence, you are able to make out which principle means what. Okay. So the point is, in natural languages, the meaning of a particular word is not conveyed only by just that particular word, but also by the words around them. Okay. So against my principle, okay, school's principle. So its meaning is being conveyed by the words around that particular word. So this window or these words around these words is known as the context. Many a times it is referred to as context. Okay. So this is the idea behind co-occurrence matrix. So it does not only captures the so to find the representation of a particular word, what it will do is, in the corpus, it will fix some window length 2. Okay. So what do I mean by fixing window length 2? Let's say I want to find the one hot representation for this word against. what I'll do is I'll look at two words. So I have a sliding window of length 2. So now there can be two slightly different interpretation of windows. I'm not very sure which one is being referred in this course, but I'll tell you both the interpretation, and based on where you are using it, you can have. Okay. So a two-length window around the word against can be that you look at two words before that and you look at two words after that. Okay. You will refer to this as two-length window around, let's say, against. Okay. There is another way where how you can define a two-length window. That is, in a two-length window, you will only have two words. Okay. So this would be a two-length window. Again, this would be a two-length window. Okay. So in two-length window, this time you will have is and my for against. Okay. So one definition I gave you where you will have 5 words, and another one you will have only these 2 words in two-length window. I think this red one, the later one, is being used in this course, like, right. So these are used in different applications. I have seen different people using different notions. I am not sure it was explicitly defined in this course, but you can use based on your application. Okay. So let's say if we stick to the second definition, what we will do is we will look at all the two-length windows. Okay. And we will count the co-occurrence of word like occurring in that particular window. Okay. So for example, in this, I'll have is and against occurring once together. So for example, if there was one more word over here is, and there is against, so I'll have entry 1 over here. And similarly, for all the co-occurrences with word is, I'll have entries over here. For all the co-occurrence with against, I'll have entries over here, and rest of the entries would be 0. So it also counts the number of times it is co-occurring. So that should you also that thing you should also keep in mind. Okay. So this is something that we define as co-occurrence matrix, and that will depend on your window length. Okay. So right now, the first example that I gave you, in that you had equal number of context and equal number of words. Okay. So for every word, you checked its co-occurrence with every other word. Okay. So this matrix, let's say if you had n words in your vocabulary, then this matrix would be n cross 1. And if n is large, this matrix would be very large. So what we can do is we can smartly choose our context. Okay, so what do I mean by smartly choosing our context? So we can remove some common words from context. Okay, so common words like is, are, a, the, even if you remove these kind of words, these count won't make a lot of difference. So it would actually help you to get better representations, because if you look at let's say word is included over here. Okay, what will happen is, so the word count in this particular column would be very high. So your vector would be slightly skewed towards these common words, and hence the representation that you will get won't be very good. Okay, so this is one thing. Okay, so this is one thing. Second thing is, there are few issues related with this particular method. First thing is, as I mentioned, the size of matrix would be n cross n, right? So every vector representation, so every row would correspond to the vector representation of that particular word. So if you look at human, this particular row is the vector representation of human. Okay, so if you want to make some prediction on this word human, this is the vector that you should pass to your network to learn further task. Okay, so the downstream task or the underlying task. And another issue is that it's still very sparse. Okay, so there are few entries which are non-zero and many entries which are zero. So these are two issues. Okay, so some fixes that people have suggested is that we can remove the frequent words. Okay, the second fix is related to the skewness that I just talked about. That let's say if you have some common words included in your vocabulary or context to be more precise, then you will have vector representation skewed towards these common words or frequently occurring words. So what you can do is you can threshold your count. Okay, so even if you, let's say if you threshold your count to 10, even if you are getting count greater than equal to 10, still you will write the count as 10. Okay, so this is another fix that you can use. Okay, last thing that people have suggested is that this is PMI. Okay, so what is PMI? So the intuition behind PMI is rather than just looking at the count of a particular pair, you normalize it with the count of word multiplied by the count of context. Okay, so if there is some frequently occurring word, for example, let's say A, okay, then its count of W comma C would be high, but the count of that context would also be high. So this will sort of normalize this thing, so it won't let it grow very high. That's why we would be able to avoid the skewness. Okay, any doubt till this point?
Sir, explain about second point, sir, threshold.
Okay, so what do I mean by threshold? uh, I'll draw a matrix, right? I'll just draw a matrix. This is cat, dog, is, and truck. Similarly, here also we have cat, dog, is, and truck. Okay, so if you intuitively look what can be the, let's say we take window to be k is equal to 2, or let's say we take window to be k is equal to 3, then cat, there is a very small probability that cat and cat will occur together in a window of 3. So let's take this as 0. Cat and dog might occur together. Let's take this thing as 2. Okay, cat and truck is very less likely to occur. Still we can take it as 1. But cat and is, there is a very large chance of it occurring. Let's say it is 15 that we are getting. Okay, so what will happen, this is your representation for cat. Similarly for dog, this is like, let's say 0, this is 10, this is 0, this is 12, sorry, this is 15 because this has to be symmetric. This is 0 and this is also, let's say 12. Okay, so this is 1, 0, 12, 0. Okay, so your matrix looks something like this. Now if you look at these entries are very large as compared to your other entries. So whenever you are doing some underlying task, let's say later you want to classify based on these particular representations of vector that you have got. So this is the vector representation of your cat. Okay, so this is highly skewed over here. So it will be highly influenced by this particular value 15. Okay, so we don't want this thing to happen. So what we will say is we will threshold the count by 5. Okay, so even if my count is 5, what I'll do is I'll replace that particular count by 5. The count over here was 15, but I'll replace this by 5. Similarly at all other places. Okay, so I'll replace everything by 5. Okay, so this is something that is known as thresholding. Okay, any other doubt? Okay, so I'll sort of rush because I am looking at the time, it's already 50. So there are a lot of topics to cover today, so I'll try to slightly be quicker. Okay. So now, if you look at the definition of PMI, there is a term count of W comma C, right? There is a possibility that the count of W comma C is 0. Okay. So for example, a word like mobile and a word like soil. Okay. So word like, let's say, telephone and soil. These are highly, there is highly less chance that these two will occur together in any corpus. Okay. So there are cases where you can't have count of W comma C to be 0, and log of 0 is definitely not defined. It is sort of close to minus infinity. So we don't want this thing to happen. Another thing is, you can't have count of W and count of C to be 0. So you might wonder, like, why are we not worried about count of W and count of C? The reason is, if they are elements of your vocabulary, then it would have occurred at least once. Okay. So that's why we are not worried about count of W and count of C being 0. We are just worried about count of W comma C being 0. Okay. So what we can do is, if our count of W comma C is greater than 0, then we can stick with our regular PMI. For all other pairs, we can define the value to be 0. So this PMI is between W comma C. If my count is greater than equal to 0, then I'll define it to be PMI itself. If it is 0, then I'll define my PMI to be 0. Okay. Then there is something that is known as positive principal mutual information, that is positive PMI. So this is defined as, if my PMI between W comma C is greater than 0, then I'll stick with my original PMI. Otherwise, I'll define it to be 0. So the case where your count is 0 and we assume that PMI is minus infinity, that will fall into second category and we'll define this PMI to be 0. So everywhere we will take our PMI greater than equal to 0. That's why it is called as positive PMI. Okay. Here are few questions based on it. The first question, actually, I'll mention the method. We don't need to solve this completely. Okay. So the question is, we are given the following corpus of word. Okay. So the first question is, what is the size of vocabulary built using this corpus? So to build a vocabulary, you just need to pick unique words. So one might try counting it. Let's look at the first two lines. This is given a sound clip of. Okay, so let me use something else. So what will you include in your vocabulary? You will include given. You will include a sound clip of. Now a is repeat. We just want unique, person or people. Speaking, separate it into two words. Okay. So if you are just using the first row, this is the corpus that you might have obtained. Oh, sorry, this is the vocabulary that you might have obtained. So somebody, if just counts all the unique words in this particular paragraph, he'll know the size of vocabulary built for this corpus. Okay, this is not at all useful, so I'll just skip. It was there, so I included. Now suppose we create a co-occurrence matrix using the corpus called M. So my co-occurrence matrix is denoted by M. So the question is, what is the value of M of given comma I? So it is asking in window length 2, okay, how many times given and A are occurring together? Let's look at this corpus and we'll try to find out. So this is one window length of 2 where given and A are occurring together. This is another. This is another. I don't see any given anywhere else. Okay. So these are only the three instances. So in co-occurrence matrix, that particular value would be 3. Okay. Okay. Any doubt till this point? Okay. So now if you look at this vector representation, still the problem is that the dimension of these representation are pretty high. And second thing is they are very sparse. Okay. So one proposed technique to tackle this problem is to find a lower dimension representation. So what we want to do is, let's say we have n dimensional representation. We want to find a k dimensional representation where k is very less than n. Okay, so you want a lower rank approximation of the vectors that we have obtained. So we know one method to find low rank approximation. So if you have a matrix X, where we are now using positive pi, so this is not pi, this is pi. Okay. Then we can use singular value decomposition to decompose into three vectors, and let's say if this is your singular value decomposition, this is your u1 sigma v1 transpose. If you just take this yellow highlighted part, okay, this gives you a rank 1 approximation to X. So in your this co-occurrence matrix, for your co-occurrence matrix, you can find rank 1 approximation of your co-occurrence matrix by just taking this much part. Okay, if you take two sums, you will get rank 2 approximation, right? And so on, you can obtain rank k approximation. Okay, one thing that you should see over here is this sigma 1 is just a vector. Okay, what is dimension of your u1? So this matrix is m cross k. So u1 is this has only, okay, so u1 is a vector. So your vector, this is m cross 1, right? Similarly, your v transpose is one row, and there are n columns, right? So this is 1 cross n. So size of this matrix is again m cross n. So the size of your vector does not change, but the rank or the dimension of your vectors have reduced if you use SVD decomposition. Okay, so now the only advantage that you would get is, like, if you are storing these matrix, then you can store it with lesser number of entries as compared to your earlier. But let's say if you want to pass this to your some neural network, then again your input layer will still have high number of input dimension. Okay, because the size has not reduced, size of your representation has not reduced. Second thing is, if you use lower rank approximation, then it was shown empirically by the prof that you have lesser number of sparse entries. Okay, so you have a slightly more meaningful representation if you use these, like, lower rank representations. Okay, but the problem that we are still facing is that it is good for storing, but the length is still of size of your vocabulary. Okay, so one thing is that if you look at your x transpose, so let's say this is your x. Okay, just give me a second. And this is your x transpose. This is x, this is x transpose. So let's say this is my representation for first word. This is how my representation for first word look like, if you remember this co-occurrence matrix. So a row would correspond to a representation of that particular word. Okay, and a column would correspond to a representation of your okay, so representation of a context. Okay, so if this is my row 1, this is row 2, this is row 3. right? So X transpose, so this would be R1, R2, and so on. Okay. So what would be the entry of my XX transpose? So first element would be R1 dot R2, sorry, R1 dot R1, then R1 dot R2, and so on. So what this XX transpose matrix is giving is that it gives you the cosine similarity between two vectors. Okay. So if you have constructed a sort of sorry, uh, if you have constructed a co-occurrence matrix, then XX transpose gives you, you can see my screen, right? I think it's frozen. Okay. So your XX transpose gives you the similarity between your representations. So let's say you have representation of cat and you have representation of dog. Then the ijth entry of your XX transpose would give you the similarity between these two vectors. Okay. So so now what was suggested is, so this, let's say this X hat represents your K rank approximation of X. Okay. It can be like written as a singular value decomposition for this matrix X hat, and you can rearrange just to obtain this much. Okay. So rather than choosing, so X hat as your representation, if you choose just u sigma, okay, let's represent this by W word. If you just use this much for your representation, then also you preserve the similarity between two like two vectors. Okay. So what do I mean? I'll just say it in a very layman term so that I can explain it better. Is that, let's say if you used representation based on just your SVD, okay, so you obtained some X. Okay. Now what is the role of this X? Okay, this X would be, let's say, passed into some neural network, then you will obtain some result. Okay. And the beauty of this X representation is that you can find its relation with other vectors. Okay. So let's say if you have X cat and X dog, you can find its dot product to check how close your dog and cat is. Okay, I'll just come back to this portion. Before that, let's do one thing. Okay, then I think it will be much more clear. Okay, okay. So this thing is called as evaluating word representation. Just give me 2-3 minutes to explain this, then we'll go back to where we were. Okay, so evaluating word representation is how do we evaluate the quality of your word representation? Okay, so one method that is not mentioned or was discussed in the course that you can do is, so what is the role of representation? Okay, what is the role of learning representation is that you want to do some underlying task. Okay, for example, you wanted to classify some comments that people have written. You want to classify that comment, whether that is a positive comment, that is a negative comment, or that is a neutral comment. Okay, so the underlying task is classification. But to do classification, what you did is, first you converted your review, whatever review that you had, to some vector, and then you pass that vector through some neural network, to obtain the result, whether that is positive, negative, or neutral. Okay, this is your underlying task. So one way to evaluate your quality of this word representation is to check the to check your performance on the underlying task. So what do I mean by that is that you train your classification model also based on this vector representation, and then you see how is your accuracy on this classification task. That will tell you the quality of word representation that you have. Okay, this is one thing. Another thing is there are three methods that that has been proposed by professor in this course. First one is the semantic relatedness. What does semantic relatedness means is that if you have, let's say, words cat and dog, you will ask human being to like give a score. What is the relationship between dog and cat? Let's say human being has given score as 0.8, and the vector representations that you have find, the cosine similarity between them is 0.7. Okay, so these are close to each other, these are fine, right? So you will do such thing for every pair of words. Okay, so cat dog, cat truck, and so on. So you will get a vector of S human. You will get a long vector of S human carrying all these kind of similarities, and you will have S model also. Okay, then you can find correlation between these two vectors to find whether the output of your model and what a human being thinks is same or not. Okay, this is one method to check the effectiveness of your representation, the representation that you have got is good enough or not. Okay, so one thing that I want to emphasize over here is when you have the vector, you have used its dot product with another vector to check the quality of your representation. How effective is your representation? You are just slight more of interested in the dot product between these two vectors. Okay. Another thing is that there is something known as synonym detection. So how do you do synonym detection? You have let's say vector representation. This is VL, this is VU, VB, VR, and VC. So you will find the dot product between VL and VU, then VL and VB, and so on. Whichever gives you the highest dot product or the highest cosine similarity, that particular one you will choose as your synonym. Okay, whichever is a synonym in this. I'm not saying that this is a synonym. Okay, so that one you will choose as your synonym, and the accuracy of choosing your synonym would be the quality of your representation. Okay, so second thing is that this also depends on your dot product. Okay, last task is something that is known as analogy. Okay, and I'll make a comment which is not very, like, I won't provide any proof, but I'll make some comment here. Okay, analogy is like the way a brother is related to a sister, what is a grandson related to? Okay, so you can find that word by this method. So you take the vector of your sister, you subtract it from vector of brother from here. So let's say this is vector of sister, this is vector of brother. The subtraction would give you a sort of direction in which you can reach from here to there. You can keep that direction intact, and you add it to V of your grandson. Okay, let's say this is grandson, then it will, you are adding sort of similar amount in that direction. So you reach some vector V, you find the corresponding word to this vector. So there is a possibility that this point does not correspond to any word. So you will look at the nearest word that is possible to this vector. Let's say this is the nearest word representation of some word, and you will relate that thing to grandson. Okay, so few, I would say 1 year or 2 year back, there was a app that was very common, in which if you entered your face, it would give you 2 3 images. One was how would you would have looked when you were a child, how would you have looked when you were a, how would you look when you will become old. Okay, you had this kind of app, if you remember, that used this kind of technique only. Okay, so it had a lot of data of people who were young as well as who were old. So they had some representation of young, they had some representation of old. So they found v young minus v old, and then they added to your so this is your v your representation of young. Okay, so this is, and then whatever representation that they got, they gave you that as your output. Okay, so this is how they were working. So these tasks are useful, finding vector representations are useful. Okay, so one thing that I have made clear is for the first two tasks, if you had just this dot product between vectors, then you would do good. Okay, and for the last task, you had some sum and minus over here. Okay, now let's get back to what we were discussing. What is W word and what is W context we were going to. So what this particular derivation means is, if you had SVD and you obtained vector x cat and x dog, okay, and now if you just take u sigma, okay, so you represent this W by u sigma, and your new representation is, let's say, x hat cat and x hat dog, then the dot product between x hat cat and x hat dog is same as x cat and x dog. Okay, and this u sigma now has this vectors x that are over here. These are k dimensional vectors. Okay, so just a small recap, that your x that you had, if you did singular value decomposition, they were low rank approximation, but their length were still n. But now if you just take u sigma, okay, now just go above, your u is m cross k, okay, and your sigma is k cross k. So this u sigma that you will get is k cross sorry, m cross k, right? So what is the now, so you have m words and k columns. So what is the length of one representation? Length of one representation is only k now, and k is very less than n. Okay, so if you use your W word being just u sigma, you can get a very less, so smaller length representation. So earlier you had n length representation, now we will have k length representation, and your k is much lesser than n, and it is doing same job for you, because the dot product between these two vectors and those two vectors are same. And if you recall the first two tasks that we had, that was semantic, okay, or the synonyms detection, they only were dependent on dot product. Okay, so if you use these representation on these kind of tasks, you will still do very well. This is the point that I'm trying to make. Okay, and for analogy detection task, you might not do very well if you use this SVD based technique to find W word and W context. Okay, now W context here would become just your V transpose vector. Okay, because your X was U sigma V transpose, you can use the rest of half as your representation for context. Okay, so I have jumped from here and there. Was I able to make this thing clear? Why do we stick to W word as our representation for word rather than going for the complete this X matrix? This is how SVD learns. So what it will do is, it will take a W word as U sigma, and its row, every row would correspond to a vector representation for that particular word. Okay, similarly for context, so what is the dimension of k? Sorry, V transpose is k cross n. Okay, so if you take your V context as V, this would be n cross k. So now for every context, you will have a representation of dimension k. okay, or length k you can say. Okay, remember that your x that you had, this is m cross n. That means you have m words and you have n contexts. Okay, usually m would be larger than n. Okay, any doubt till this point? So this also has one disadvantage, that there is no learning of parameters involved. Okay, another disadvantage that I can write is this eigenvalue and eigenvector computation is not very computationally efficient. Okay, so you have to calculate all the eigenvalues and all the eigenvectors, and then you have to reach these vector representations. So you don't have any intermediate vector representation. For example, if you learned using some neural network algorithm, then at every step you will have some representation or other that you can use. Okay, but in this SVD based methods, you don't have intermediate representation, so you will have to do all the computations to reach to your vector representation. Okay, so computationally also it is expensive. Any doubt in this, like whatever I have discussed about SVD based method? Okay, we have a question. Question is, after doing SVD on a co-occurrence matrix, we find that Mij, okay, has the highest value in ith row. Okay, so the co-occurrence matrix we have done SVD, so we have obtained some x hat. So its row would represent words. So ith row means this is vector representation. So for some word, let's say cat. Okay, where m is the low rank representation of co-occurrence matrix. Choose the current. So what it says that Mij, so there is some j, so this entry is highest. Okay, so what does this mean? Okay, so first option says word j occurs many times in k-span window of word I. So although this is a low rank representation of your original co-occurrence matrix, but because it is an approximation to your original co-occurrence matrix, so it will sort of try to preserve the properties of your original co-occurrence matrix. So in your original co-occurrence matrix, if this value was highest, then that would have meant that in a k-span window of word I, there are a lot of occurrence of word j. Okay, and similar thing would be true over here also. Okay, now second point is word j and word I have high cosine similarity. Okay, and this thing is also true. Okay, because you have high value in your I and j position, then if you take your xx transpose, so this entry would have larger value. This is not true because your co-occurrence matrix would have a sort of symmetric thing, and this also does not make sense. Okay, okay. So these were some classic. Till now we have just covered some classic NLP techniques to find word representation. Now we will try to move to neural network based techniques to find word representations. Okay. So before we go there, any doubt in this? Okay, so today we have, I think, lot of more content to cover. So that's why I'm not stopping a lot. So if you have any doubt, I request you to please unmute yourself and ask. Okay. So yeah. So first method, neural network based method that we are going to talk about is something known as continuous bag of word. Okay. It is also similar to what we have done in like co-occurrence matrix method. Okay, but it's slightly different. Okay, so what we want to do over here is, so if you are given a context, so this green thing over here that we are given, if you are given a context, we want to predict the next word that we can have. Okay, so if you want to, like if you look at this example, when you type in your phones, you always have some suggestions on top. Okay, so what can be the next word? This is a useful task. First of all, it is a useful task in itself. Second point is, if you are able to find a vector representation such that you are able to predict the next word, then you, like if you intuitively think, that vector representation in itself would be very good. Why? You are able to predict what would be the next word in the sentence. Okay, so that is not a very trivial kind of a task, right? So for that to happen, you should be able to find good vector representation. Okay, so what is the idea behind it? So idea behind is that you would be given some context, so that you would be given words before that, and you have to predict the next word. Okay, this is the task. Okay, so this is an example where you have only one word and you have to predict the next word. Okay, so what you are given is, you are given with the context, that is you are given with the words around your word that you want to predict, and you have to predict the next word. Next word is your original word. Okay, so how does this work from a neural network perspective? You will have a one hot encoded entry. Okay, that you will map to a k dimensional vector. Okay, this k dimensional vector h, right, would in fact would be your representation for your word sat, for example, over here. So you will learn some weight. After that weight, this h that you will obtain, this is your actual representation of your k dimensional vector. Okay, okay, sorry, this would be your actual representation for your word sat. This would be your word representation. Then you will pass this representation. So till now, if you look at this particular portion, this you can sort of, like when you are training your neural network, at that time you will do it in one flow. But if you want to intuitively see this thing, you can break it into two parts. First part is, till this point you are finding an appropriate representation, and the second part, you are sort of predicting the next output. Okay, okay, so this is one thing. Okay, I'll try to explain this slightly more detail. Whenever you have a neural network, you can write, let's say this is your first layer, this is your second layer. Okay, so you can write these weights in form of a matrix, right? That you know, right? You have done 9 lectures on this course, so you know that you can write it in form of a matrix. The same matrix over here is represented by W context. Okay, so that same weight matrix over here is represented by W context. Okay, so if you have an input, I'll change this notion to Rn, where V is n. Okay, so this is, let's say, n dimensional vector that you are having as an input. Okay, so what is the dimension of this W? So if you have input, okay, so what is the dimension of this matrix that we will have? So there is a slight, I think, notational problem over here. If you see that here you have input a k dimensional vector and you are outputting an n dimensional vector. Here you have an n dimensional vector and you are outputting a k dimensional vector. But whatever is written over here, at both the places we are saying that the matrix belongs to the same dimension, which is not actually true. Okay. So you will have this matrix to be n cross k. Okay. So this weight matrix is your n cross k. Then you can take W context to be transpose of this matrix. Then this thing is correct. Okay. So this would be transpose of this matrix. Okay. This is first thing. Now, if you look at the input vector, okay, input vector is nothing but the one hot representation. Okay. So let's say you pass your just give me a second. You pass your input. Let's say your input is x through this vector. So what is the output that you get when you pass your input through this weights? So what would be the representation for this? Okay, so I'll just write it slightly more so that you understand what is going on over here. I'll just take one input. Okay, and two outputs. This is W1, W2. Okay, so you can write it as, so if you want to write it as number of inputs into number of outputs, the size of this, if you want to write it as 1 cross 2, how should you write it? This should be 1, this is W1 comma W2. Okay, so how do you obtain the output? Let's say your input is, I think I'm messing things up. Okay, so if your vector, if your matrix W is the matrix of weights, okay, so what is the output that you will obtain if you pass, let's say, x through it? Okay, right now your x is just a scalar, right? So you can just obtain something like, let's say this is 1 cross 2. Okay, so and your x is, let's say, 1 cross 1. So what you can do is you can do W transpose x to obtain your output, right? Then your W would be 2 cross 1, and you can multiply a 1 cross 1 vector, and then you will have two outputs, right? So same thing is happening over here also. So if your W is something like this, then what you are doing is you are multiplying your W with your input vector x. Now, as I said, W transpose is nothing but your context vector. So this is W context into x. Now, if you look at this x, x would be in form of a column. Okay, x would be your n cross 1. Okay, x would be n cross 1. So, and only one of the entries in your n cross 1 matrix is non-zero, and that is also equal to 1. So what would be the output of your this W context into x? It would be just the ith column of W context. Okay, so if you represent that thing by, let's say, UC, okay, where U is your word and C represents that you are taking its context vector. So this H that you have obtained is nothing but the ith. So here second entry is your 1. So ith would mean second entry of your weight matrix. Okay. Now, what would be the output of this particular thing? Okay. So again, this is K. This is n. So what is the size of weight matrix? If you write it in this way, what is the size of the weight matrix that you would get? Size would be k cross n. And to find its output, what you would get is, what would you do is, so you would do W transpose of H, that is you will do W word transpose H, right? This is what you will do. Okay, so now your W word like symbolically has vector representation of V1. Let's say this is V1, this is V2, right? So if you take its transpose, it would be something like V1, and you are taking its dot product with your H vector. Okay, this is second thing. So the output entries that you will get just before activation would be a form W word transpose H, right? And then because you want to predict the probabilities on top of it, you can take the softmax operator on top of it. Okay, so loss function that we define on top of this is the cross entropy loss, and we want just this entry to be 1. Okay, yeah, we want only this entry to be 1, and all the other entries on your output we want it to be 0. That's why your cross entropy reduces just to minus log yw. So what was the formula for cross entropy? It was summation minus pi log q I, but pi is for everything except for one entry is 0. So everything rest reduces to 0, and only this particular entry is left as 1, and the output or the qi corresponding to that thing is represented by yw. Okay, now what is yw? Yw is the output of this particular layer. Okay, so this particular layer was this matrix being multiplied by H. What was my H? H was UC. So every entry over here would be of form, this would be of form UC dot V1, this would be UC dot V2, and so on. So a particular entry over here is of form UC dot VW, and if you take the softmax function on top of it, so it would look something like exponential of UC dot VW divided by summation of all these form of UC dot VW. This is how we do softmax, right, to convert it to probabilities. Okay, so this is how one can obtain the loss function. Just one thing that you can see over here is, in the loss function also you have a dot product of like vectors of this particular form. Okay, now there is one problem with defining this kind of loss function. The problem is, let's say your V has 10 million words. This is V is your set of all vocabulary. Okay, then you will have to calculate this dot product, their exponential, and then sum it up for 10 million entries. Okay, so the last layer also is very computationally expensive. Okay, so if you remember different types of activation functions that we learned in the last lecture, there I said that the softmax function is computationally expensive. Especially it becomes computationally expensive when you are summing it over the large number of entries. Okay, so this thing is computationally expensive. This you should remember right now. So just a very small recap. I have done a lot of I think hodgepodge over here. So I'll just recap for you what you are going to do if you are training a neural network in general using this method. Okay, I'll just copy this image for a second. Give me a second. Okay. Even if a lot of things were not clear, just listen to what I'm going to say next. Okay. So what you're going to do is you're going to input a one hot representation. Okay. And you want to predict what is the next word. Okay. You input a word and you're going to predict what is the next word. So how would your last layer should look? Your last layer should look like probabilities, right? So this is a very simple neural network where you have this is, let's say, input layer. Then there is one hidden layer, H. Okay. And then there is an output layer with softmax activation. This is just that you should remember when you talk in perspective of neural network, that you have one hot representation as input, then you have an intermediate layer, then you have an output layer with softmax. This intermediate layer, you can see it as word representation, and you might use it for other tasks also. Okay. And the loss function that you're going to use over here is your cross entropy. Because of the softmax, you get terms like exponential of some, let's say, output is OI divided by summation I belong to V, J belong to V, exponential of OJ. Okay. This OI or OJ would look something like UCW dot VW. This is because of the nature of this input that you have over here. Okay. This input only is such that it will, this H that you will obtain will depend only one of the columns of your weight matrix over here. So that's why you have something of form UC multiplied by VW over here. Okay. And people relate this to the representation of context and this to be the representation of your word. Okay. So this is the simple basic idea. And when we started with, I told you that what we want to do is, given a context, I want to predict the next word. But whatever we have discussed till now is related to only one word being the input and predicting the next word. So if you have more than one word as the input, you can concatenate their one hot representations. So if, let's say, this was 0, 1, 0, 0, 0, something like that, and this was 0, 0, 0, 1, and then lot of zeros. So you can just concatenate these two vectors and pass the same algorithm over here, and you will obtain your result. Okay. This is from a totally implementation perspective. Okay. And this method is known as continuous bag of word. And the major disadvantage that it has is that it has to do softmax operation, and the denominator sum is very large. So you have to do the sum over all the possible words in the vocabulary. So the denominator sum is pretty large. So this is computationally very expensive. Okay. Any doubt in this? I know I have not very cleanly explained this. Yeah, I should have thought about it, but I thought, yeah, I have not very cleanly explained. But if you have doubts here and there, maybe we can discuss that, and then it would be more clear for you guys. Okay, if there is no, then we'll go to something that is known as skipgram. Okay. So skipgram is totally sort of opposite of what we did in continuous bag of word. What we do in skipgram is, if you are given a word, we want to predict the context around it. Okay. So for example, the word is he sat on a chair. So given the word on, you should be able to predict a and a chair. Okay. So you want to find a representation H so that you are able to predict he sat on a chair. So whatever you see in this dark blue thing, even in the above figure, these are sorts of your vector representation that you are trying to find. Okay. These can be used for other tasks also, not only this task. These are the methods by which you find your representation, and this can be also used to find like you want, so you can take out these vector representation and you use it to train other tasks. Okay. So how does this skipgram model works is, so you have some input using some, so you have some weights connecting these two layers, and then you reach to something that is your h, okay, and then this h is connected to a layer where you will get y1, y2, y3, y4 as your output, and so on, okay. And how many y's you will get? You will get y is equal to number of words in your vocabulary, okay. So now if you want to find the probability of he given your word, or you want to find the probability of sat given your word, okay. So you want to maximize these values which would occur, and for other values you are not interested. So for one word, what we did in cross entropy was minus log ywi. Now you want all these four outputs, so you take sum over all these four outputs. He sat chair. So how many words you want in the context, you need to decide that. So for I is equal to 1 to the number of words that you want, and you will sum it over all those bag of words, okay. So because now you again have this this y hat wi would again be obtained in the similar manner using your softmax. So you have same problem as you had in bag of words, that it is computationally very expensive, okay. So to overcome this problem, you have three methods. I have 20 minutes left. I'll try to explain these methods at least, okay. So there are three methods that people have proposed over time, so which overcome this problem of summation in the softmax algorithm, okay. So first solution that people have proposed is known as negative sampling, okay. So what is the idea behind negative sampling? I'll just come to negative sampling. Okay. So let's say uh, you have some dictionary of words. Okay, so you have some corpus of word. Okay, there would be some pairs that would occur together. Okay, for example, in the paragraph written over here, you make a pair like sometimes in. So you write these kind of pairs, sometimes in. Okay, then you write in the. Okay, then the 21st. Okay, so this way you construct a dictionary. Okay, you represent it by D. Okay, so this D contains all pairs of words that are occurring together. Okay, similarly, you can have a sort of a pair of words which are not occurring together. Okay, so this contains W comma C such that W and C occur together. And you can have a D dash such that W and C do not occur together. Right? So because you know which words occur together, you can create D dash which do not occur together. Okay. So what we want to do is, I want to create this kind of a small network. Okay, so let's just ignore this for the time being. What I want is, let's say this is my VUC and this is my VW. If my words are occurring together, I want this output, let's say I take both these vectors, I take their dot product and I pass it through a sigmoid activation. I want my output to be 1 if W comma C belongs to, if this pair belongs to D. Okay, I want this thing to be 1. for all the pairs that are occurring together. Okay. So now what negative sampling proposes is, so negative sampling says you not only consider the words that are occurring together, but also include some negative samples. Okay. So it says that you include, let's say, for every positive sample, you include k negative samples. Okay. So it says that if W comma R belongs to D dash, that is these words are not occurring together, then the probability should be equal to 0. Z should be equal to 0. This should be high. Okay. In this case, we want this thing to be high. That is, my sigmoid function should be close to 1. And we want a sigmoid function close to 0 if my words are random words. Okay. So what is the objective that I have is that for all the positively occurring pair, so if my W comma C belongs to D, then I want this probability to be maximized, right? And for others, I want this probability to be maximized. One very small thing is that over here, we won't consider all the negative pairs, because if we go on comparing all the negative pairs, again this product would be very computationally expensive. First thing is that if you want to maximize these kind of products, this trick you might have learned in machine learning also. If you have product of probabilities, now the probabilities are between 0 to 1. Okay. So if you want to maximize this thing or minimize some product of probabilities, then many values between 0 to 1 getting multiplied together would lead to values very close to 0. Okay. So what people do is, rather than maximizing this product, people maximize the log of this product. Okay. So you would be maximizing summation log of these probabilities. Z is equal to 1 given WC if W comma C belongs to D, plus summation W comma C belongs to D prime log of probability of Z is equal to 1 WC. Okay. Now if you consider all the pairs W comma R belonging to D dash, again this would be computationally very expensive, right? Then you won't get any advantage of switching from skip gram to your negative sampling. So what we will do is, we won't look for all the pairs W comma R random words, but rather we will look only at, let's say, k times the number of positive samples. Now this would be much lesser. Okay, this would be much lesser. So this thing would be justified. Also, people have proposed other methods to sample W comma R based on their like occurrence in the corpus. Okay. So if some word is more frequent than the other, then the more frequent words are more likely to be sampled as a negative sample as compared to a less occurring word. Okay. And this probability Z is equal to 1 given WC is modeled by your softmax function. Okay. That is, you just want to find the U transpose UC transpose the VW or VW transpose UC. So your this sum that you had is replaced by, you want to maximize W comma C belonging to D, okay, log of sigma of UC transpose VW plus W comma R belonging to D dash log of sigma of UC transpose VR. Okay, so this would be V, okay, sorry, this would be UR transpose VW. Okay. So this is the term that you want to maximize. Now you see there is no softmax involved over here. So if you just use this as your maximizing function and you learn this UC and VW, okay, again this UC and VW you have to learn, okay. So if you use this kind of things, this is known as negative sampling, and you can learn these things, okay. So again, how do you learn these things? So if you look at this skip-gram model or whatever models we have looked above, okay, the only thing that will change is the loss function in the last layer. So this loss function in the last layer would be replaced by these quantities, and you will obtain your UC as your H. This would be your UC, and VW would be again your rows of this particular weight uh, matrix. Okay. So these things would again be learned via neural network only. Okay. So this is one thing. This is something that is known as negative sampling. Second method is known as contrastive estimation. This is a very simple method. After you have obtained your H, or I would say UC, okay, what you want is probability of on, I want it to be more than the probability of some random word. Okay, so you sample some random word which is not co-occurring with SAT, okay, and what you want is from your representation you want only one output, that is your S. You want S of on to be greater than S of, let's say, abracadabra, okay, and you just don't want it to be greater, you want something like S of greater than on is greater than equal to S of abracadabra plus some M, okay. So if you maximize, if you impose this kind of condition, this is known as contrastive estimation, and this is a pretty simple method, okay. Okay, so I'll come to hierarchical softmax. I'm not sure if I will be able to do globes today. Okay, I'll at least do hierarchical softmax. Okay. Okay. So now again, here also the idea is simple. We just want to replace the softmax law based loss that we had with some other kind of loss. Okay. So you have some input, you have some intermediate representation VC. Okay. Then from these weights that you have learned, you can obtain, this should be UC. Okay, this notion is UC. I think there is a typo. This notion should be UC, and the representations that you have learned from here is VI. Okay, for this particular node it is VI. For this it would be VI plus 1. These would be based on the rows or the columns of your weight matrix, the way you write your weight matrix based on that. Okay. Now from here we want this to learn. I think the notions are absolutely flipped over here. Okay, so if you look at negative sampling, okay, here for the context part, okay, for the first half, we use the representation as UC. Okay, now here I think they have replaced this U by V and V by U. Let's stick to what they have used only. Okay, let's say my hidden representation that I get till this point is VC. Okay, then I want to sort of do something better than softmax. Okay, so the idea for my this hierarchical softmax is that from the output layer, so this is my output layer. Okay, this output layer will have n outputs, right? These are n outputs. Okay, so I'll start constructing a binary tree. So the tree would have these two connections going to this layer, and then so on reaching to a one node. So you'll construct a tree like this. Okay, leaving your this leaf node, your every leaf node is corresponding to one output in your output layer. Okay, you leave this last layer. On the layers above this, you define a vector associated with every node. Okay, so the way professor has started, he has denoted this as u1, this is u2, this is some u3, so you can represent this as u3, you can represent this as u4, and so on, and he has represented this as some uv. Okay, so every node will have some vectors associated with it, and we want to fine tune these vectors also. Okay, so what would happen is, so what is the objective? Objective is that given your context vector, words that are occurring, we want to maximize its probability. So what we want to do is, we want to maximize this probability of word given your VC. So if you are given with some hidden representation, we want to maximize the probability of correct words. Okay, now how is this probability modeled? That is in our hand, and I'll tell you how it is modeled over here. Okay, so you start with the topmost node. Okay, let's say your correct output is this. This is your correct output. Okay, so if you move to your left side, then this pi function, there is a pi function that is defined. That pi function takes value 1. If you move on your right side, then this pi is defined as 0. So if you want to reach from here to here, then your pi would be defined something like, it would be a sequence. It would be a binary represented sequence. It would be something like 1, 0, 0. Let's say if you want to reach here. Okay, so this is pi 1, this is pi 2, this is pi 3. These are all the components of pi vector. Okay, this is how your pi looks like. Okay, so this probability of this word, now because every word w over here has a unique pi representation. Okay, so this can be written as probability of that particular sequence given VC. Okay, so we wanted to find the probability of word given whatever input I have or the hidden representation that I have. I have changed that thing to probability of this particular sequence. So every sequence corresponds to a unique word. So there is a one-to-one correspondence between these two. Okay, so if you write your w or you write your pi, that don't makes a lot of difference. Okay, also we can model this thing, that what is my probability of pi of wk, okay, given my some vc. Okay, so this we can model. How we can model this thing is that as I said, every node except of the leaf nodes will have some vector representation ui. So probability that ith element pi I would be 1 given your some vc. This is given your vc, right, is given by softmax between ui and vc. Okay, this is how you can model. Okay, then probability pi I is equal to 0 given vc can be again modeled as this can be modeled as minus of ui comma vc. Okay, so you can see this derivation over here. This would lead to just this being between minus ui comma vc, and then your probability of pi of wk given vc would be just the product of pi i's wk given vc. Okay, so because you are able to find for individual component, if you just take the product of all of these, then you can obtain the result. and this is how you optimize. So you want to again maximize this thing. You want to maximize this probability. You will again take the log, then you will convert everything to sum, log times something. But now you will have only sigma, that is your sigmoid activation function. So you again don't have any softmax in this, and this is how you overcome the softmax computational problem in this case. Okay, we'll try to look at some of the questions in the time that we have left. Okay, so here is a question. We add incorrect pair into our corpus to maximize the probability of words that occur in the same context and minimize the probability of words that occur in different contexts. What is this technique called? Okay, so as we discussed few moments ago, what is the technique in which we use some of the words that do not occur together? So we try to maximize the probability of word occurring together, and we try to minimize the probability of words that occur in different contexts or words that does not occur together. This kind of method is known as negative sampling. Okay. Okay, the second question is, suppose that we are learning, okay, so we haven't done globe. I'll see if we can do, and then we will come back to this question. Okay, so last question, let's try to first do, and then we'll look at other two questions. Which of the following techniques are used to evaluate word representation learned by a vector? Okay, so we saw all these three methods were used to evaluate the quality of word representation, so all of the above is the correct answer. Let's quickly look at the globe. I'll just give you an idea what it is, and then we'll look at that question. Okay, so what we do in globe is, so we want to find the vector representation for vi and vj. We want to find the word representation for word j and word I. Okay, so we also have a co-occurrence matrix. Okay, so what we want to do is, I'll give you a very sort of abstract idea. Okay, you can use it to find a representation of any arbitrary data set. This is sort of abstract, and then I'll link it to globe over here. Okay, so what happens is, you have your data set in some original space. Okay, let's say this is called space S, and you have some Rn space. The one of the core idea of finding a representation is, if two items are similar over here. Okay, if two items are similar over here, let's say this is my item 1, this is item 2. If two items are similar over here, what should be my expectation is, when I find its representation in Rn, let's say this is my representation for Rn, this is my representation for R2, then these two vectors should also be similar to each other. Right, this is not very much to demand. Like, if two vectors are similar in the original space, what I want is that they should also be similar in my embedded space or the representation space. Okay, so this space is also known as embedding space. Okay, representations are also known as embeddings. You might hear it sometimes. Okay, so now the choice is what similarities you want to define over here. Like, if you are in original space, you can have many similarities that you can define. For example, in words, you can define co-occurrence in some window, or you can choose any arbitrary similarity that you want to define. And in Rn also, you can have a number of similarities. For example, Euclidean distance. You can also have a cosine similarity. So what you want is, the similarity between I and j should be similar to, let's say, cosine between. So I want this to be close to vi transpose vj. Okay, this is what I want. Okay, so for globe, what these people have suggested is that this Sij that I want to define in my original space, this thing is nothing but probability of j given I. That is, what is the probability if like I am encountering A, then I'll encounter J in some next K window. Okay, that is K and J occur in a window of K. k length window. This is the similarity that we define in globe. Okay, so what is this probability of j given I? This is nothing but log I can write. So this is co-occurrence of I and j divided by occurrence of I. This is the probability that if you are given I, what is the probability that j would occur in k context. So number of times you have encountered I, and number of times both of them have occurred together. This is the probability, right? So again, this can be written as log of xij minus log of xi, right? And you can, this dot product in the embedded space are same, right? Vij transpose and Vj transpose Vi are same. So this should also be equal to log of P of I given j, right? From here you can obtain log of xij minus log of xj. If you add both of them, what you would obtain is that Vi transpose Vj is nothing but this is log of xij minus half log of xi minus half log of xj. This is what you should expect. Like if you have similarity exactly matching with each other, this is what you should expect. Okay, but in reality, this won't be very exactly same. Okay, next thing that people have done is that they have replaced this xi and xj by some hyperparameter that they want to learn. Okay, so they have replaced this xi by this. So if they move this thing to this side, this would be Vi transpose Vj plus Bi plus Bj is equal to log of xij. This is what we want. So if we want this, then we can sort of minimize this squared error to minimize the error between xij and this particular quantity. So this won't be exact equality, but approximately they should be equal, and then we can minimize this. This is the idea behind globe. So what was the idea in terms of what we talked about over here? So idea was the similarity that we are using over here is co-occurrence. If two words co-occur together, then we want their vector representation to be close to each other in terms of cosine similarities. This is the idea behind globe. Okay. You can similarly change some notion of similarity over here and similarity of notion over here. You will get some other vector embedding technique. Word embedding technique. People have done this and obtained a series of embedding techniques. There are many embedding techniques in literature. Okay. Globe and word2vec are famous ones. Okay. So here is a question. Suppose that we are learning a representation of words using globe representation. We observe that the cosine similarity between two representations are very high. Okay, which of the following statement is true? Okay, so what is the cosine similarity? Vi transpose Vj. Okay, what we want is plus Bi plus Bj. This should be approximately close to Xij, right? This is the like the idea behind globe. Now these quantities are given to be very, very small, and this cosine is given to be large, right? So that would mean this Xij would be large. How large it would be? So what is the maximum that you can see here? So this is the most probable answer. So 0.8 is the correct answer. Okay. So this question I haven't covered. Okay. So the question is, what is the what is the similarity between SVD and word2vec technique? Okay. So probably I can do this in the beginning of next class. I'll just take 4-5 minutes before the next topic to do this. Today I won't do this question. Okay. So I'll end the recording, and if you have any doubt regarding